Hey Chicago, last chance to get tickets to the Data Skeptic Live event. Tuesday, May 15th at the Mendoza College of Business on Michigan Avenue. Hope to see you there. Link in the show notes, found at dataskeptic.com.
Welcome to Data Skeptic. Our mini episodes are gentle introductions to concepts related to artificial intelligence. These short discussions are meant to serve as a primer for the topic. Learn more by reading our show notes at dataskeptic.com.
All right, Linda, today we're going to discuss game theory. Now, I mention that to you every so often. Do you know its formal definition?
Maybe when there are players and you estimate what the players will do and what they are thinking.
You're along the right lines. I'm going to be a bit more specific. So game theory is the study of equilibria-based solutions. At least that's what it is to me. An economist might give you a slightly different definition, but for data skeptic listeners, that's the best definition in my opinion. So what does that mean? Do you know what equilibria are?
You always want things that are equal in the world.
Oh, no,
Reaching
not
a state
necessarily
of
equal. No, you can have equilibria which are very imbalanced and unfair.
So what is it then?
An equilibria, it's a pair of strategies where neither participant has an incentive to leave the strategy. You know, there could be a predatory relationship, like let's say like a really mean landlord who doesn't take care of the property and a tenant who's paying too much for the property. If it's off balance, eventually that tenant should leave, right? But if there's some reason why like it's bad, but it's just good enough that the tenant is incentivized to stay, maybe it's close to their work or something like that, then maybe it's not ideal for either person, but neither of them will switch.
Switch.
Yeah.
Switch states.
Right.
Leave the game.
Yes. Well, switch your strategy. In the renting strategy, I guess the player, the renter, has two strategies: to pay the rent or to default. If we think more generally, that might seem a bit ridiculous in real life because we just would like wait for the lease to run out. But more generally, like a local merchant who sets the price of things, they have to set them in an equilibria, hopefully. Or at least people will claim that the price tends towards an equilibria. Because if it's too high, people won't buy enough, so you have to lower it. If you lower it too far, you'll see it flying off the shelves and you'll know you can raise your price again, right?
So in this case, what's an equilibria with the prices? Where they're willing to buy it?
It's where, so just enough buyers will continue to buy it, and they're not incentivized to go elsewhere. Mm-hmm. Or if there's two stores that have identical things, they have to price competitively.
So what's your definition of equilibria?
An equilibria is a pair of strategies where nobody involved has an incentive to switch their strategy.
Okay.
So a lot of people learn about equilibria in the context of prisoner's dilemma and stuff like that. Psychologists are really into certain game theoretic stuff. What's it doing on Data Skeptic? Aside from the fact that it is a very mathematical underpinning to it all, it has to do with artificial intelligence specifically, in that another way of defining it is the study of perfectly rational, intelligent agents. So if you created an AI that had, all the resources it needed, as much hard drive, as much memory, all that stuff, and an infinite amount of time to figure things out, two perfectly intelligent agents with common knowledge of perfect rationality would always arrive at some equilibria solution and then start playing it.
No, that's fine. But what's the math underlying it?
Well, the basics of it start with like John Nash's work on zero-sum games, and you just put sort of the contingency table of rewards, and you can show whether or not there's an incentive to switch. And he proved that there's always some mixed equilibria. Mixed is where you would randomize a little bit. Oh, so let's do another game. You know rock, paper, scissors? Mm-hmm. Or they call it Rochambeau other places. Mm-hmm. The optimal strategy, the equilibria strategy, is to always randomize what you choose. You don't have any advantage in trying to be sneaky or always play a certain pattern. Because if you exhibit a pattern, your opponent can see it, and the degree to which they're able to predict it, they'll just take advantage of it. If you both play perfectly randomly, you're going to win 1/3 of the time, you're going to lose 1/3 of the time, you'll tie 1/3 of the time. So that's your expectation, right? You should win, lose, and draw 1/3 each. If you try and get an edge, I'm going to win 50% of the time, you can only do that by having a non-random strategy. And then if it's non-random, someone else could predict it, and then they could take advantage of you, and you'll do worse, you see?
I don't think humans are perfectly random, so...
Well, yeah, that is a big problem in those games. We don't seem to have reliable random number generators inside of us. So,
but I'm sure they could try their best.
Yeah, they can try their best. Maybe there's like mental techniques for being as random as possible, but you're right. People are really bad at making random numbers up. That's how a lot of accounting fraud is actually caught.
You told me.
Yeah, people like Benford's Law and stuff. But anyway, back to the perfectly rational stuff. This is the criticism I have of game theory if you really want to get into it. The first is that we assume a common knowledge. Maybe we should define common knowledge. Common knowledge means we both know something, and we both know that the other knows it. So like there's a half a donut left in the kitchen that you brought home. We're both aware that it's there. We both know that the other one knows that it's there.
Or you think it's there.
It better be there.
As of this morning, you thought it was there.
So whoever eats it wins. It's a zero-sum game. We don't both win. One wins, one loses. I don't know what the strategies are going to be exactly for that, but it's common knowledge because we both know that we both know.
Right.
So,
or like in chess, the common knowledge is the board and every piece on it.
Oh, good point. You're exactly right. You don't know what's in the other person's head, but you know the state of the game. With that example, it sounds obvious, like, oh, who cares about assuming common knowledge? It sounds like a very basic assumption. But actually, as we talk about more and more complex agents, for some problems, there exist equilibria. Like, here's an interesting thing. There are a lot of papers that come out that prove some situation has a mathematical equilibria. But to understand that, you have to be a game theorist and know a lot of background in it. So the idea that I would meet a smart person walking down the street and they would know the right equilibria solution, it's very low, right? They're probably not a game theorist. Common knowledge of perfect rationality is kind of a fiction in some sense. Perfect rationality means you will always have enough resources to find the optimal solution or find the equilibria.
I don't know. How does one find the equilibria?
Well, usually through an algorithm. Game theory is becoming more algorithmic now. In the early days, you'd make kind of like a table of who has this advantage or that advantage. And then you can derive, you can kind of compare those situations. But as people started looking at bigger problems, the combinatorics got hard. And also you introduce probability. So talk about like negotiating a house, right? We know if we want to buy a house, what our budget is. We have some flexibility on it. The person puts the house on the market, the seller does, at a selling price, which hopefully represents about what they think it's worth. But maybe they'll sell lower. Maybe they want more than that. In our particular area, a lot of people are coming in above asking on houses and stuff, right?
Oh, yeah, we're in LA. As people say, it's a hot market.
At the moment, anyway.
For now.
Yeah. Going into a negotiation, you each have private information, right? Like we know our private valuation, and the seller knows their private valuation.
Of the property.
Yeah, but we don't know their idea. Something in their mind, they're thinking, hey, I'll sell this if I get an offer of X. And maybe they list it above X because they want to make as much profit as possible. And they don't know what we're approved for, or they don't know what our budget is or anything like that. So we both have private information.
Yeah.
But there's also public information. We both know the price of the home and stuff like that.
When it was last sold and the price.
Yeah, which may or may not be relevant. And then we can seek out new information, like we can get inspections and stuff like that, and that improves our knowledge and would maybe affect our evaluation of it. So we have, since we don't know their private information, we have to have a probability distribution over what it might be, right? We don't know what the seller would be willing to sell for, but we know a range maybe, and we have a belief about what it would be, that sort of thing.
Well, I assume the range is the listed price.
Well, that's one number. It's not a range.
Yeah, but hopefully it falls within the range.
Yeah, hopefully it falls within the range, yes. But the range could be big.
Well, I mean, we like to think the listed price is how much the seller wants to sell it for, but that's not always the case in LA.
Or if it's competitive, it could go above.
Yes.
Or if the seller has a sharp discounting, like they really need to move quickly, they might be willing to sell for less because they have a contingency of some kind.
Yes.
Usually in game theory, you represent a thing like that with a discount factor, which is to say, $1 today is better than $1 tomorrow. But what
does that mean? Well, I guess I'd rather have $1 today than tomorrow.
Yeah, of
then
course.
I can spend it today.
Right. So then let me say it this way too. What would you prefer, $1 today or $1.01 tomorrow?
Yeah, I guess I could wait for 1 cent tomorrow.
Well, what about $1 today or $1.02 in 7 days?
7 days. It's a better deal to have 1 cent in 1 day.
Well, that deal's off the table.
I'm not sure.
Like so many of you, my love for learning didn't stop when I finished school. And one of my favorite ways to be a lifelong learner is with the Great Courses Plus. The Great Courses Plus is a wonderful streaming service that gives you unlimited access to learn from award-winning professors about anything that interests you. Of course, my bias is towards math and science and things like that, but there's a great library of history, art, music topics, even hobbyist things like photography, chess playing, or maybe you want to learn a new language. there are over 10,000 lectures to enjoy. You can watch from your TV, your laptop, or take it to go with your tablet or smartphone. Here's a great feature for Data Skeptic listeners, especially those of you that commute. You can stream just the audio portion of the lecture on the Great Courses Plus app. And of course, it doesn't work for every lecture, but you'd be surprised how often that's helpful. Very recently, I've been listening to Surveillance State, Big Data, Freedom, and You. This is a really relevant course for data people. Paul Rosenzweig explores the issues of surveillance, from ethical dilemmas to the science behind data analytics, examining the questions of how to move forward while preserving our rights to privacy and freedom. So we've arranged for a special limited time offer. You can get 1 full month of free unlimited access to enjoy all of their lectures. You have to use the special URL. It's thegreatcoursesplus.com/data. Why don't you start your free month today to check out the service? Once again, it's thegreatcoursesplus.com/data.
It's a better deal to have 1 cent in one day.
Well, that deal's off the table.
I'm not sure. Depends what I
Right.
want to use the dollar for. Exactly.
Yeah, and how urgent you are. Like, if you are late for something and you need $1 to get on the bus, that dollar might be very valuable
Yeah,
to
I
you.
just might be like, I don't care. One example is when I fill gas.
Uh-huh.
I used to always drive out of my way to go to the cheapest gas.
Yeah, it's not worth your time.
But then, the cheapest, we save about 10 cents a gallon max. We have a Prius, so it only holds 12 gallons. So at 10 cents max, that means every time I fill up, I save $1.20. So then now I ask myself, before I drive X number of miles out of the way, I go, is it worth $1.20? And if it's not, I go to the one that's right there in front of me. Because I go, well, actually, I'd rather pay $1.20 just to do this and be done.
Yes, you have to account for your time and the opportunity cost.
But before, I'd be like, yeah, I saved money. But when I actually calculate how much I saved, I was like, it wasn't enough.
Yeah, it costs money to do that.
It wasn't enough.
Right. I'm glad you see it that way. That's true. What's happened as you've gotten older is your discount factor has changed.
What's a discount factor?
If you delay reward, how much better the reward has to be later to be justified, right?
So how much is and if the delayed reward is worth it?
Yeah. So if you're trying to sell a house, right, the fact that you're trying to sell it generally means you have to do something next. It's not like you just sell a pair of sneakers and it doesn't matter. Like, that's tied into bigger finances. And if it doesn't sell for 6 months, that's inconvenienced you in some major way, and you're paying for it the whole time, right? So there's a question of well, if you get a low offer, is it better to accept now, immediately, or hold out for a better offer later?
Right.
And there's a probability distribution. There's, mathematical ways to approach this stuff. Down to the specific negotiation, that's where you'd get into more of a game theoretic approach. So you don't know what the discount factor is of the seller. You have to have a belief over that, and you have to know your own, and you actually want to hide your own, because if the seller knows your discount factor, then they can reason better than perhaps they could if they didn't know that information.
So what is your definition of a discount factor?
Usually you make it a very simple thing mathematically. A common way to do it is to pick some number, like maybe 0.9, and raise that to some variable, let's call it t for time. So at time 0, the beginning of the game or of the selling of the house or whatever, anything to the 0th power is 1, so you don't discount. But at time t equal 1, maybe that's 1 day or 1 week, whatever it is, well, now it's 0.9 to the 1th power. And then 2 units of time, it's 0.9 squared, and that keeps getting smaller and smaller. So that is a common way of modeling discounting. You could do it other ways too, but usually the papers I read anyway, they take some very simple mathematical model of it, which in fairness is a criticism. In the real world, people have very disjointed discounting, right? Like, people will be like, I have to sell in 21 days no matter what. So it's like always 1 and then a step function to 0. But mathematically, you model it with that little exponential thing I described, a constant raised to t. So game theory's application to artificial intelligence is that if you build these perfectly rational agents, then the smartest thing for them to do when they interact with one another would be to find equilibria-based solutions. Because as we said, if you're in an equilibria, neither person has an incentive to leave it. In fact, they both have an incentive to preserve it in some way.
Right. Well, I think we already do, assuming you think I'm an intelligent agent.
Oh,
Are
yeah.
you saying I'm not an intelligent agent as you've defined it?
Linda, I don't know how to answer this without hurting your feelings. You are what I would call a boundedly rational agent.
What does that mean? Now I'm confused.
Because you don't have...
I'm neither offended nor complimented. I'm just befuddled.
You don't have infinite computational resources, so you couldn't possibly find the most optimal solution in all situations. You're only capable of solving it with what your immensely powerful and wonderful brain within its, very vast capabilities, but finite capabilities. So you are bounded by your biology.
Well, any player of the game theory
Yes.
is bounded by the same biology.
Oh,
So
sure.
it goes without saying.
And this applies in interesting ways too when you talk about bots and stuff, like people doing like little change the price on Amazon things. Those are expensive to run on scale. So you generally program them in a simple way so that you don't rack up a lot of computing costs. So it's boundedly rational by cost there. And it might be like simple rule-based systems can sometimes have advantages. But yeah, in terms of people, we are vast but always bounded agents.
Vast yet bounded. That
Yeah.
should be our neon sign hanging in our living room. And then when people walk in, they'll be like, "Do you mean space?"
So let me get this straight.
I think we should do this.
You're
we should get
open-
this neon sign that says vast yet bounded.
You're open to that for the living room.
Yes.
Our living room that we live
Yes.
in, where
maybe
people
the
come
dining
over
room
and
area.
see it.
What do you think?
I think you're drunk.
It could be blue and have some kind of like galaxy reference, like a star ending.
This sounds like an idea I would have that you would reject.
I thought you would love this idea.
Yeah, I'm into it, but I
You
don't know if
are?
you're serious.
Oh, yes. Listeners, we may have this one day.
Yeah, we'll see. Keep listening and find out. We talked about how people are boundedly rational, but a lot of modern game theory takes that into account in studies, like the behaviors of agents that have some limits on them of some kind. So that's
So do
interesting.
you imagine what they know and don't know? How do you do that?
Mostly, it's an area that I'm sure many creative grad students are doing cool stuff in right now. And if you're one of them, shoot me an email. I want to hear about your work. But the way that comes to mind for me is like I would study something like an L-space agent, like it only has logarithmic size of memory, or is like only going to compute polynomial algorithms or linear algorithms, has some sort of limit like that. Or maybe it's using probabilistic data structures because it's looking at streaming data. Some like computational thing that describes the limits of what it could figure out and how it could compute its policy.
Sounds like you'd use this game theory with to consider racism and sexism.
Tell me more about what you're thinking.
I don't know. You just said for example, a polynomial, blah, blah, blah.
Yeah.
I was like, what if we could play out a game theory where someone's racist or sexist and see how it would end up to see?
So you're not entirely off base. That is something that potentially works well, yeah. Oh, we're getting to another point here that I wanted to discuss in terms of valuation. So I am coming back to your point though. Earlier I had described that there's a private valuation people have, like the seller has a price, the buyer has a price. But actually, people have preferences that are more than just price. Maybe the most greedy people, it's all money, but you would want to live at a house that maybe is near a good restaurant, and some people don't care about that. Or, you have a relative nearby, access to public transportation. Realistically, everyone is negotiating over a vector that describes their valuation. It's not just the price. That matters a lot. But another person it might be important to them that they have a backyard that's enclosed for a pet. Not every house has that. And some do, and it's not like a selling point. There isn't a special list of pet-friendly houses, at least I don't think so. So you don't even know the dimensions over which the other person's negotiating. However, getting back to your sociology little thing here, there are interesting regressions people do where they will say, can we calculate the value of public transit? And they'll calculate the distance from a home to the transit and try and introduce that as a regression variable. So if the regression assigns some weight to it, you can maybe compute, if you put the right model in there to smooth it out, you can compute by distance how much people will pay more for being near public transit.
So does it work?
Yeah, maybe, if
We should use it for ours.
But see, for that stuff, you have to assume that the model is correct. It's always that sort of regression is a little wishy-washy to me. No offense to people that do that.
You don't want to use it?
I will look at it, but I don't know that that's convincing entirely for me because there's so much variance left unexplained in problems like that. You could just be overfitting. Or, how do you measure the value of the distance. Is it like a linear distance? Is it a exponential decay distance? You have to make these sort of technical choices in the regression. And if those technical choices don't apply to the real world, then what good is your result? I would have to be really, really serious about that to build it up enough that I would be confident in it, you know? I'm very skeptical of models like that. But in terms of like you were bringing up racism, off the top of my head, I don't know how you model it that way, but yeah, you could look at what are rational choices people make and include that as a hidden variable and look at problems where race was known versus not known in some transaction or something like that. It's possible to study those things with mathematics, yeah.
Okay.
I don't know about game theory specifically because racism is inherently irrational. There's no rational basis for it. So anyone who does that is an irrational agent. So maybe game theory doesn't really describe it.
Can't you could be rational even if you're racist.
I don't think so because there's no rational reason to arrive at that conclusion, you know?
Well, racism doesn't mean it's rational, but the person can still be rational.
For other topics, yeah, for sure. Especially when they have incomplete information. Not all of game theory looks at this, but the parts that are most interesting to me are when the games have incomplete information, so the players don't know something about each other. And for complete information games, there's a lot of known solved problems. For one-sided incomplete information games, like maybe the seller knows everything but the buyer doesn't, those games also have some known equilibria solutions. But to the best of my knowledge, two-player incomplete information games don't have very many general solutions, if any. So even though game theory seems to be the right path, of yet the field hasn't developed enough to give us the tools to approach things on really complicated problems. But it's growing, and there's cool stuff coming out of it. So a big field, actually, and lots of variations that we've just talked about ever so briefly. But again, game theory is what?
I don't know.
Is
it class?
Class plays a role. It's the study of agents that act in equilibria.
In equilibria?
Yeah.
I thought they meant in rational ways.
Yeah, they're perfectly rational agents, and perfectly rational agents would always tend to arrive at an equilibria. At least that's what a game theorist will tell you.
And equilibria is defined as both agents get something out of it.
Close. Their strategies, that pair, is in equilibria if neither player is incentivized to leave, to change strategies.
To change strategies.
Yeah.
Or not play the game. Is changing strategies not playing the game, or is there a way to change strategies while still playing the game?
Not playing the game would be a change. So if you think about like, you know, an employer-employee situation, the employee might feel like, oh, I don't get paid enough, but apparently they're paid just enough that they won't quit their job, right? So
as it always happens to be in the real world.
So that's an equilibria while it lasts, that neither participant is incentivized to switch strategies. Although maybe at some point the employer should say, hey, we're going to give this person a raise because we want to stay in equilibria. And we think it has drifted or whatever.
Yeah.
But yeah, so key takeaway, it's about equilibria. Equilibria is a pair of strategies, or three if there's three people. Most of the math is done over two. And then a lot of interesting variants dealing with boundedly rational agents and incomplete information and common knowledge and stuff like that.
Bounded yet rational.
And so the overlap with AI is that these are good behavioral strategies for intelligent agents.
So you're saying we should behave like these agents? Sort
of. First, I'm not saying that game theory equals artificial general intelligence. Far from it. But when you get into specific, narrow environments, game playing, negotiating, stuff like that, game theory starts to come into play when you have two or a finite number of agents that are going to interact. They have incomplete information. They have objectives that may or may not be totally aligned. They need to find equilibria-based strategies because otherwise it's all going to tumble apart. Well, thanks as always for joining me, Linda.
Thank you, Kyle. Data Skeptic is a listener-supported program. To support the show, visit dataskeptic.com and click on the membership tab.